So far, we've been learning to differentiate functions. A function is something that looks like this, maybe that, but all of them, if you were to put a vertical line through them, only have one y value per x value. However, it's also possible to differentiate functions that give graphs that look like a circle, or maybe an ellipse, or maybe a sideways parabola. And in this case, if you put a vertical line through them, at some points there are two x values. So these are not classified as functions, but they're still graphs. This is where something called implicit differentiation is useful. An explicit equation is something that looks like y equals x squared plus 3x, or y equals e to the power sine x. They're all written as y equals. An implicit equation, however, looks more like x squared plus y squared equals 4, where it's no longer written as y squared. Now you could rewrite this equation as y squared equals 4 minus x squared, and then take the square root, but remembering that you've got plus or minus. And you could differentiate this, because of the plus or minus, you have to split it up into y equals positive 4 minus x squared, and y equals negative 4 minus x squared, and it becomes a lot more of a hassle. To differentiate a function that has a y that's not just y equals, we are going to follow the same rules that we normally have, but we need to recognize one extra thing. And for that, we're going to start with the equation y equals ln x. I taught you that this differentiates to 1 over x, but I didn't say why. We're going to use this as an example on how we use implicit differentiation, and therefore why the rule comes about. You could rewrite this as e to the power y equals x using the log exponential transform. Now if I were to differentiate both sides, I know that e to the power of x differentiates to e to the power of x, so I can use the same rule. To differentiate an e, I copy it down, and then times by the derivative of the power. Now the thing we have to recognize is that when I times by the derivative of y, well, y differentiates to dy dx equals, and the differentiation of x is 1. To get dy dx, I'm going to divide by e to the power y equals 1 over e to the power y, and since in the line above e to the power y equals x, this is equal to 1 over x, which is the rule that we have learnt previously. So, how do we differentiate x squared plus y squared equals 4? Well, we're going to differentiate x squared normally, that goes 2x. Now, to differentiate y squared, we're going to pretend that the y is in brackets. To differentiate that with brackets, you bring the power in front, you rewrite the bracket, and you times by the derivative inside the bracket. Timesing by the derivative inside the bracket is dy dx, and this equals 0. We can bring the 2x to the right hand side, we get 2y times dy dx equals negative 2x. Dividing by 2y, we get dy dx is equal to negative x over y. So the main rule that we need to learn, that has come from both of these two examples, is that when we differentiate something with a y, you're going to follow the same differentiation rules, but just times by dy dx after. So, perhaps we wanted to find the equation of the normal to the curve 2x squared y plus 3xy squared equals 16 at 1, 2. Well, to find the equation of a normal, I've got to first differentiate to find the gradient of the tangent, and then I can apply some rules to get the gradient of the normal. So differentiating. Both of these are products, which means we have to use the product rule for both ones. So product rule says differentiate the first. If we treat the first as 2x squared, then that will be 4x times the second plus the first, 2x squared, times the derivative of the second. The derivative of y is dy dx. Then that's the first one, so now we've got this next term, plus the derivative of the first is just 3 times the second, plus the first, times the derivative of the second. So y squared will differentiate to bring the power in front, reduce the power by 1, and times by dy dx. That will be equal to 16 differentiates to 0. In order to get dy dx, I'm first going to move all the terms that don't have dy dx to the right hand side. It gives us 2x squared times dy dx plus 3x times 2y is 6xy times dy dx equals negative 4xy minus 3y squared. I can factorize dy dx, leaving 2x squared plus 6xy equals negative 4xy minus 3y squared, which means that dy dx equals negative 4xy minus 3y squared all over 2x squared plus 6xy. Now I have my equation of my gradient for the tangent. I can sub x equals 1 and y equals 2, since there's an x and y in both of these. It leaves us gradient of the tangent equals negative 4 times 1 times 2 minus 3 times 2 squared all over 2 times 1 squared plus 6 times 1 times 2. That gives you negative 8 minus 12 in the numerator and 2 plus 12 on the denominator, or negative 20 over 14, which is negative 10 over 7. That's the gradient of the tangent. The rule for the gradient of the normal ended up being inverse and change the sign. So inverse we get negative 7/10, change the sign we just get 7/10. Now, we know that the gradient is therefore 7/10. I know that x1 is from the question 1, and y1 from the question is 2. That's everything we need. So y minus 2 equals 7/10 x minus 1, giving us y minus 2 equals 7/10 x minus 7/10. Or y equals, maybe put it in decimal, 0.7x plus 1.3. And that there is the equation of our normal. Now, say we wanted to find a second derivative, for example. Let's look back at the original question, x squared plus y squared equals 4. To find the second derivative, we apply the same rules, but we've just got to be very careful. First derivative, we get 2x plus 2y times dy dx equals 0. You can simplify by dividing by 2 to get x plus y times dy dx equals 0. Now, to get the second derivative, we need to differentiate this again, but we've just got to acknowledge that this here is a product. So we have to therefore use the product rule. So differentiating, x goes to 1, plus the product rule says differentiate the first, dy dx times the second, dy dx, plus the first, y, times the second differentiated. Dy dx differentiates to the second derivative. That's still equal to 0. That gives us 1 plus dy dx squared plus y times the second derivative. And from here, dy dx is equal to negative x over y, which means I can make a substitution, 1 plus negative x over y squared plus y times d squared y over dx squared equals 0. That gives me 1 plus x squared over y squared plus y times d squared y over dx squared equals 0. Now I'm going to bring the 1 and the x squared plus y squared to the right hand side. Y times second derivative equals negative 1 minus x squared over y squared. When I divide by y, I finally get the second derivative is equal to negative 1 over y minus x squared over y to the power